Hello everyone, my name is Modukanele. I'm an instrument specialist who's focused on radiation technology to characterize materials. The Botswana Institute for Technology Research and Innovation, BITRI, is a parastatal under Ministry of Tertiary Education, Research, Science and Technology. The institute has been established in 2012 to conduct needs-based research and development in focused areas. The mandate of BITRI is to identify, develop, adapt appropriate technology solutions that provides sustainable, innovative solutions through co-creation and collaboration in line with national priorities and needs of Botswana. BITRI is utilizing ionizing radiation technology equipment under the Nanomaterials Division in the Center of Material Science section. CMS has a wide spectrum of specialized equipment that includes the XRF, the XRD, the XPS, and the SCM, which are the main radiation technology equipment. BITRI has adopted a radiation protection program in 2016 and has been licensed by the Radiation Protectorate Department of the Government of Botswana. The Institute has ensured compliance to radiation protection program, in that safety officers, users, and workers wear full body dosimeters, in that equipment is kept under maintenance plan, and that the equipment is serviced by authorized engineers who are certified by the manufacturer, and ensures that all time the BITRI radiation protection program is adhered to and revised in each and every year. We have in BITRI Gemini SCM 500. The SCM 500 is classified under low-level background radiation equipment and does not require licensing and monitoring by the Radiation Department of Botswana. The SCM has got field emission gun that generates high electron beam that is focused on the sample. The system setup has high-level safety features and housing a heavy metal shielding that does not pose any radiation leak to the users. Trained specialists are authorized to operate and to care for the system. The system is widely used in having good understanding of the morphology and composition of materials, as it's essential for understanding their behavior. These are the specifications of the Gemini SCM 500, and it has the following detectors: the secondary electron detector in the chamber and in the inlets. It has the BSC detector in the chamber and another detector in the inlets. It has the STEM detector, which is the scanning transmission electron microscope module, which is added to the scanning electron microscope. It has the EDS detector, which is the energy dispersive spectrometer, and the wide dispersive spectrometer. I have highlighted the main ones, but there are other extra detectors that are in the system. The EDS and the WDS X-ray spectrometers enables one to carry out elemental composition as well as the elemental mapping of the sample. Therefore, one is able to spatially analyze and view the distribution of elements in the material. Here is one of the illustrations of a nanofiber membrane imaging, which was captured using the Gemini SCM 500 in BITRI. The image here is a section of a membrane that was fabricated within the lab, by the team that electrospins the nanofibers. This was one of the success of setting up and proving the ability to manufacture membranes that could also be used for fabricating the masks. The X-ray fluorescence spectrometer XRF is an S8 Tiger manufactured by Bruker, which is also a wide dispersive XRF. It is classified as a low radiation X-ray source. The XRF has got a rhodium X-ray tube housed in a lead shielded chamber. The system has got semi-automatic sample handler which can take 65 samples at a go. Here is the illustration of the sample bay, of which samples are placed there, 65 of them, and the system is programmed to continue the analysis. Here is the illustration of the XRF principle, from X-ray source through the filter to remove the noise signals to reach the sample, and characteristic X-rays are generated to pass through the single crystal, and the single crystal system automatically changes rotates to change the diffraction in order to determine different types of elements, which are then detected in the scintillation counter as well as the proportional counter. So there are two types of crystals here, for heavy element setup and the light element setup. The technical data of the XRF system is provided right here, and what is important is for one to recognize that the system can analyze liquids, loose powders, as well as solids, and the system has got various options of which can be improved, as well as that it has the automatic sample changer, the automatic analyzer crystals, the automatic masks. The system uses helium and PTEM gases. The S8 Tiger is a 4 kilowatt system which gives the maximum current of 170 milliamps and the maximum voltage of 60 kilovolts. The XRF analysis begins from the X-ray source to the detector, then followed by the signal processing, which is done at the personal computer. The spectrum is then assessed by a specialist who then determines the elements that are present by checking on their peaks and measuring their peak levels and accounting for the correction factors that may involve the loss on ignition, and the results are therefore given out. The Center for Material Science was engaged in one of the projects under BITRE, which was spearheaded by the Building Material Science Division, and here are the elemental compositions of the various samples S1 to S5, and I'd like you to take note of the amounts of calcium from left to right, and you will see that the amounts on the right are lower than the amounts on the left. And as you can see down here, from left to right, you see that the amounts of silica is low and the amounts of silica are high on the right. This illustrated that high purity calcium carbonate rocks have got low amounts of silica, and those which have got high amounts of silica has got low contents of calcium. Therefore, there's an inverse relationship between these two minerals, which are calcium and silica, found in the geological material. The Empyrean Pananalytical X-ray diffractometer, in short the XRD, uses the copper tube X-ray source housed in a lead shielded housing, which is over there, which has got steel chamber surrounding the system to absorb the low-level radiations, as well as the tinted glass where we can view the system while it's running. The XRD is one of the equipments where there's high regulation to the operators. They should be trained and competent personnel who are then validated and authorized to operate the system. The XRD technical specification is as follows: that it's a 4 kilowatt system, and it has its abilities to move at very small angles, that having an ability to do the success and the waxes techniques. Here is the illustration of the XRD principle. As you can see on the left, we have a high voltage source tube, which is our copper tube, and the beams pass through the solar slit and the beam slits, which directs the parallel beams towards the crystal, and the crystals give out the X-ray characteristics X-ray, which are then displayed in form of peaks as demonstrated here. Our XRD system has various techniques, which has got the phase identification and quantification to determine the composition of the monitor purity, and we have another technique, the X-ray reflectometry, which determines the thin films and the thickness and the roughness of the films, which is an optical technique here, and another technique in which we can do the success for nanostructure analysis. We also have the transmission XRD for characterization of organic materials, the transmission of XRD for nanoparticle size distribution. XRD analysis is given out in this form, that we are able to use the Rietveld technique, in which we can estimate the composition of the heterogeneous crystals that were found in the limestone material. And this is one of the illustrations on the results of the analysis. Continuing from our previous discussion about the limestone project for exploration of limestone, the XRD was also used for analyzing the samples. As you can see, we have S1, S2, S3, and S4 with inverse relationships of the quartz to calcite, which is low when there is calcium-rich material, and of which when quartz is high, there is low calcium content. Our fourth and last instrument is the Axis Supra XPS, which was supplied by Shimatsu Kratos. The XPS is an X-ray photoelectron spectrometer, which has got also high-level safety features, which renders low interaction between the user and the sample. It has automized sample handling system, and only trained and specialized users are authorized to operate the equipment. The XPS imaging reveals the lateral distribution of surface chemistry and aids further characterization with selected areas analysis. The system has various options of sources, which includes the aluminum anode, the silver anode. It also has the UPS lamp. It has the helium lamp. It also has the argon ion cluster gun and the field emission electron gun. The XPS principle is as illustrated in the diagram here. The X-ray beam source interacts with the sample, and the characteristics X-rays are directed towards the spherical hemisphere. At the hemisphere, there are two sections, which has got the spectroscopy analyzer and the imaging analyzer. The XPS is the main analysis technique. However, it also has various techniques that can be used in testing the samples, which has got the high resolution scanning field emission auger system, the ultraviolet photoelectron spectroscopy, the UPS, the ion scattering spectroscopy called the ISS, and the argon cluster gun to do the depth profiling analysis of the synthesized layered material. And generally, these are the thin films which we have been testing. XPS analysis has an advantage to determine the binding energies of elements, of which can actually differentiate the elemental states of mainly elements such as metals. You will notice that there is a difference between copper 1, copper 2, copper 3 states. Therefore, XPS can highly outline the regions of the binding energies, and therefore enabling the user to determine the binding states of a particular material and their quantifications. In this illustration, you will notice the region of interest over here, where the cadmium 3D energy levels has got a binding energy to the nitrogen at 1s, and the two together they form the cadmium ammonium salt. The Center for Material Science Research, with utilization of the radiation technology equipment, has been able to support research within BITRE in the nanomaterials, in which nanofiber membranes, nanoparticle catalysis, cold to chemicals, water filtration, foot and mouth disease test kits were developed with the aid of the use of the equipment. We also have demonstrated that we have supported building material science through the limestone exploration. We have continued to analyze the mine dump waste utilization project. We have continued to support the Kalahari Sand building block project, the specialized cement material under the BMS. We have been able to support the local institutions and those international ones across Africa We have continued to support manufacturing, construction, and mine industries. In conclusion, radiation technology remains the backbone of research and industrial material analysis. Technology safety has proven to be reliable and producing low-level radiation to users through this specialized equipment. Maintenance and upkeeping of the technology requires dedicated large funding and investment on specialized skills, such as maintenance engineers, of which we experienced a challenge during the COVID-19 pandemic, when borders were closed and the engineers are outsourced from outside Botswana, and therefore the upkeeping of the instrument became a challenge. This is one of the areas where our country needs to invest more into the upkeeping of the equipment, as well as training specialized personnel.